If I hang a spinning bicycle wheel from one end, gravity should make it fall. So why does it start turning sideways like it's dodging the floor? Try it in your head first. Picture a wheel spinning fast. You grab the axle with one hand like a handle. The wheel is out in front of you. Gravity pulls down on the wheel's center of mass, so it makes a torque. And you think, okay, torque means rotation. So the wheel should rotate downward and flop. It should fall. And instead, the wheel swings around sideways. It starts orbiting. It looks like the wheel is doing something clever, like it found a loophole in gravity. People call that gyroscopic stability, as if it's a special property, like spinning things are stubborn. But that name is dangerous because it makes it sound like there's some extra force that appears when something spins, like an invisible hand holding it up. There isn't. What's happening is simpler and more beautiful, and once you see it, it changes how you think about any spinning thing. Tops, wheels, planets, atoms, everything. Most people learn angular momentum as a number you calculate, I times omega. Moment of inertia times angular speed. And that's fine for homework, but it's exactly why gyroscopes feel like magic, because angular momentum is not really a number. It's not just how much spin, it's a direction. It's an arrow in space. And the trick is, torque doesn't push that arrow in the direction of the torque. It turns the arrow sideways. If you only remember one sentence from this entire video, make it this. Torque is not the cause of rotation. Torque is the cause of a change in angular momentum. That sounds like a small wording change. It's not. It's the whole story. So let's build this from the ground up, the way Feynman would force you to do it, by starting with something so simple you can't hide from it, and then stepping into the strange case only when you're ready. Let's start with the boring version, a wheel that isn't spinning and a torque that behaves exactly the way you think it should. Take a door, the classic. You push near the hinge, nothing much happens. You push far from the hinge, it swings. That's torque. You can feel that torque depends on where you apply the force and which direction. It's the tendency to make something rotate. Now take a wheel mounted on an axle, not spinning. Hold the axle at its end so it can rotate freely. If you apply a force downward on one side and upward on the other, you create a torque. The wheel starts rotating in the direction of that torque. No mystery. Torque points along an axis, and the wheel accelerates around that axis. That's what your intuition says. That's what every beginner thinks torque means. And it's not wrong, but it's incomplete, because in that case, the wheel had no angular momentum to begin with. There was nothing already spinning. You were creating rotation from rest. Now keep the exact same wheel, but spin it up like crazy first. Then apply the same torque. It behaves completely differently. That's the moment students usually say, okay, gyroscopes are weird. But the wheel didn't suddenly become weird. Your definition did. Because what torque actually controls isn't rotation. It controls the thing that rotation produces, angular momentum. Force is to linear momentum what torque is to angular momentum. That analogy is the doorway. If you push on a cart, you apply a force. That force doesn't directly cause the cart to have a particular velocity. It causes a change in momentum. If you push briefly, you change the momentum by an amount proportional to force times time. If you push continuously, you keep changing the momentum. Now, if the cart already has momentum and you apply a force sideways, you don't cancel the momentum. You don't stop it. You deflect it. You bend its path. That's exactly what torque does to angular momentum. But to feel that, we have to treat angular momentum as a real object in our minds, not just a symbol in an equation. Now forget the wheel for a second. Imagine angular momentum as an arrow you can hold in your hands, like a compass needle that remembers how it's spinning. Let's do this carefully. Imagine a perfectly balanced wheel spinning. Pick a direction. Say the wheel is spinning like a fan facing you, and the top edge is moving to the right. Use your right hand. Curl your fingers in the direction of rotation. Your thumb points along the axis. That thumb is the direction of the angular momentum. So angular momentum points along the spin axis, but it's not just a direction. It also has a magnitude, a length, telling you how much spin. A fast, heavy wheel has a long angular momentum arrow. A slow, light wheel has a short arrow, and that arrow lives in space, not inside the wheel. Space itself can hold that arrow because it's a vector. This is already a different way of thinking than I omega. Now ask, what does torque do? Torque is also a vector. It points along an axis as well, given by the right-hand rule from the force and lever arm. And the fundamental law is torque equals the rate of change of angular momentum, not torque equals rotation, not torque equals angular acceleration. Those are true only in special cases. The deepest relationship is the change of angular momentum. So if torque is applied for a short time, the change in angular momentum, dl, is in the direction of torque. That means torque doesn't make the wheel rotate toward torque. Torque adds a little piece of angular momentum in the torque direction. And once you say it like that, the gyroscope suddenly becomes predictable. Because in the gyroscope case, the torque from gravity is perpendicular to the existing angular momentum. That's the whole trick. You have an angular momentum arrow pointing one way, and you add a small change pointing a different way, and the result is a rotated arrow. Let's make that picture so clear you can't unsee it. Imagine the wheel's angular momentum arrow pointing straight to the right. Now gravity creates a torque, say, pointing into the screen. That means gravity is continuously adding tiny bits of angular momentum into the screen. So after a tiny time, your original arrow to the right plus a tiny new arrow into the screen gives a new angular momentum arrow that's slightly turned. It's still almost to the right, but now it's angled a little into the screen. Do it again. Another tiny bit into the screen. The arrow turns more. Do it continuously, and the arrow rotates smoothly. And if the angular momentum arrow rotates, that means the wheel's axis rotates. That rotation of the axis is precession. So the wheel doesn't fall because gravity doesn't act to remove the spin. Gravity acts to change the direction of the angular momentum, and the change is sideways. The wheel responds by turning its axis sideways. It's not resisting gravity. It's obeying gravity, exactly, mathematically, mercilessly. It's just that the obedience looks like rebellion because you expected the wrong kind of motion. Here's the rule. Nobody says out loud, torque doesn't tell the wheel where to go. It tells the angular momentum arrow how to rotate. Now, if you've never seen angular momentum as an arrow before, you might think this is just a clever drawing trick, a way to get the right answer. But it's not a trick, it's the real mechanism. To prove that, we need to show that the wheel has no choice, that if you try to make it fall directly, you would violate the torque angular momentum law. Let's go back to the hanging bicycle wheel, the famous demonstration. You hold one end of the axle. The wheel is spinning. Gravity pulls down at the center. The lever arm from your hand to the center makes a torque. The direction of that torque, using the right-hand rule, is horizontal, perpendicular to the wheel's angular momentum. So dl dt is horizontal. That means L itself is changing direction horizontally. That means the axis sweeps horizontally. That's precession. So the precession rate is basically how fast torque can bend that angular momentum arrow. A big torque bends it quickly. A big angular momentum resists bending. It doesn't stop the bending, it just makes the bending slower. That is already an intuition you can feel. A spinning wheel is like a fast-moving bicycle. If the bike is barely moving, you can turn it sharply. If it's going very fast, you can still turn it, but it takes more distance to bend the path. Same with angular momentum. So why doesn't it just fall? Because to fall would require the angular momentum arrow to point downward. And for it to point downward, you'd need a torque that changes it downward. But gravity's torque doesn't point downward. It points sideways. So gravity cannot directly produce the falling motion you imagine. Now pause. That's a weird thought. Gravity wants the wheel to fall, yet gravity's torque can't aim the wheel downward. So what happens instead is the only thing gravity can do. It turns the axis sideways, okay? But a skeptical mind should now ask something even sharper. If gravity can't point the wheel downward, how does the wheel ever fall at all? Because in real life, gyroscopes do eventually droop. Tops eventually fall. Wheels slow down and sag. So where does that come from? That's where friction and energy loss enter. Not as extras, but as the only way the system can change the magnitude of angular momentum or allow components to shift. Without friction, an ideal gyroscope could precess forever at a constant tilt angle. But before we add the messiness of reality, we should understand the clean core. And we still haven't answered what most people really want. Yes, the vector story is beautiful, but it still feels like a mathematical explanation. It's like saying because vectors, People want to know, what is physically happening inside the wheel that makes it move sideways? So let's open the wheel and watch the forces. If you could freeze time and watch the forces on different parts of the spinning wheel, you'd see why falling isn't the natural response. Imagine the wheel as a bunch of little masses going around in a circle. At the top of the wheel, the mass is moving, say, toward you. At the bottom, it's moving away from you. On the left side, it's moving down. On the right side, it's moving up, depending on how it spins. Pick a definite orientation so we can talk clearly. Now, gravity pulls down on every piece of mass. That downward force changes the momentum of each mass, but the effect of a force depends on the direction of the momentum it acts on. This is like a moving car. If the car is moving forward and you push sideways, you don't suddenly make it move sideways. You change its direction. You curve its path. Now on the spinning wheel, the masses at different positions have momentum in different directions. Gravity acts downward everywhere, so it changes those different momenta in different ways. Focus on one mass element at the top of the wheel. Suppose it's moving toward you at that moment. Gravity pulls it downward, so its momentum vector gets a small downward component. It was forward, now it's forward plus down. That means the mass begins to curve downward. Now look at the mass element at the bottom of the wheel. It's moving away from you. Gravity pulls it down. Its momentum becomes backward. Or D plus down. That curves it downward too. So far everything is curving downward, which sounds like the wheel should fall. But here's the catch. Because the masses are constrained to remain in the wheel, these changes in momentum manifest not as free falling, but as forces transmitted through the rigid structure. The wheel is trying to keep its shape. When a mass at the top tries to curve downward, the wheel must exert an internal force to keep it in the circular path. And those internal forces create a net effect. They twist the wheel. You can think of gravity as trying to pull the front of the wheel down at one part of the rotation and pull the back down at another part. But because the rotation is continuously moving those parts around, the direction of the resulting twist is not downward, it's sideways. Another way to say it, gravity applies a torque about your hand. That torque acts on a spinning distribution of momentum. A torque on a spinning momentum distribution produces a rotation of the axis at right angles. This is the same reason a spinning top precesses instead of simply tipping over. The torque from gravity is not aligned with the spin axis, and so it changes the direction of L rather than immediately lowering the axis. You might still feel that this is hand-wavy, so here's a more concrete mental movie. Imagine the wheel spinning. Now imagine giving it a small push to tilt it down. When you push a spinning wheel to tilt down, you are actually trying to reorient the plane of rotation. But because the wheel is spinning, the part that you push down is not always the same physical part. By the time the wheel responds, that bit of metal has moved around to a different position. So your downward push gets redistributed around the wheel as it spins, and the only consistent effect is a sideways rotation of the axis. It's like trying to push down on one point of a merry-go-round while it's spinning. The point you push on doesn't stay there. Your force becomes a twisting effect around the whole system. Now, all of these physical explanations are compatible with the vector law. They're not alternatives. They're the same truth from different angles. The vector picture is the cleanest. The physical mechanism is the texture. Now that we have the core, we can add the famous formula, but we'll do it in a way that feels like a reward, not a requirement. Imagine the wheel has angular momentum L. Gravity creates a torque about your hand. If torque is perpendicular to L, then it changes L's direction at a rate given roughly by the precession angular speed O, with the relation T equals OXL. In magnitude form, when T is perpendicular to L or equals T, L. Notice something. The precession rate is bigger if torque is bigger, and smaller if angular momentum is bigger. That matches intuition. A heavy wheel far from your hand produces a bigger gravitational torque, so it precesses faster. A wheel spinning faster has bigger angular momentum, so it precesses more slowly. That's why when you spin a top faster, it wobbles less and precesses more slowly. As it slows down, L decreases, so O increases, so it precesses fast. And becomes unstable. And now we can answer the earlier skeptical question, why does it ever drop? Because the ideal picture assumes torque is exactly perpendicular and the system is perfectly frictionless. Real systems lose energy, and the torque isn't always perfectly perpendicular to L. Small components of torque can change the magnitude of L, and friction at the pivot can allow the axis to drift downward. But even more interesting, the gyroscope often has to dip slightly to establish the steady precession. And now the weirdest detail. To precess, the gyroscope actually has to fall a tiny bit first. It has to buy the sideways motion. This surprises people because they imagine precession as the thing preventing the fall. But in fact, to get the correct torque-L balance, the gyroscope usually dips until the geometry is such that the torque causes the necessary sideways change in L at the right rate. You can even see this in a top U spin. At first it may wobble, a motion called nutation, before settling into a smoother precession. That wobble is the system finding the correct relationship between tilt, spin, and precession rate. So precession isn't a magical escape from gravity. It's a negotiated compromise between gravity's torque and the existing angular momentum. Gravity keeps trying to change L. L keeps pointing mostly along the spin axis. The result is that the axis can't just go where gravity wants. It goes where the vector equation forces it to go. Now let's return to the promise of the title. Nobody will show you angular momentum like this. What does like this mean? It means not as a formula, not as a memorized rule, but as a concrete thing that can be turned. So here's a thought experiment you can do right now without a wheel. Hold your hands out like you're holding a long stick. Now imagine that stick is the angular momentum arrow. Suppose it points forward. Now suppose a torque points to your right. That means the change in angular momentum points to your right, so the arrow becomes forward plus right. That means the arrow rotates toward the right. But if you look at the physical object whose axis matches the arrow, that object's axis rotates toward the right. That's it. That's precession. You can now predict gyroscopic behavior before seeing it. If you apply torque upward, the angular momentum arrow will turn upward. If you apply torque sideways, the arrow will turn sideways. The axis follows. In other words, a spinning object doesn't rotate in the direction of applied torque. It rotates in the direction of the change in angular momentum, which is in the direction of the torque, and since that change adds to the existing angular momentum, the result is a motion perpendicular to both. And if that sentence sounds too abstract, here's the compact visual. If L is an arrow, torque adds a tiny arrow. The sum of arrows is a rotated arrow. That rotation is the observed motion. So the secret isn't that the wheel resists gravity. It's that gravity can only change the wheel's spin by turning its angular momentum sideways, and sideways mud. Motion is exactly what precession is. Now, before we close, let's connect this to a broader idea, because this is not just about gyroscopes. This is about how nature uses conserved quantities and how motion reorganizes itself when you try to change something that's already moving. Anytime you have something with a big momentum, linear or angular, and you try to change it with a force or torque that isn't aligned with it, you get sideways consequences. A fast-moving car doesn't slide instantly sideways if you push it. It turns. A spinning wheel doesn't tip instantly if you torque it. It precesses. The pattern is deeper than the specific example, and it shows up everywhere. Earth itself is a spinning top. The gravitational pull from the moon and sun exerts a torque on Earth's equatorial bulge, and the result is that Earth's rotation axis slowly precesses, a motion called the precession of the equinoxes. That's why the North Star changes over thousands of years. Stars, accretion disks, spinning molecules, and even the way electrons behave in magnetic fields, these all have the same underlying theme. When something has angular momentum, the way it responds to torques is geometric. Once you see angular momentum as a real arrow in space, the universe starts looking different, because every spin, from a toy top to a galaxy, becomes a story about what can and can't turn that arrow. And maybe the most Feynman-like takeaway isn't the formula. It's the attitude. Don't accept the label gyroscopic stability as if it's a magical property. Ask, what exactly is changing? What exactly is conserved? Which vector is being rotated? What is being added? Because physics is rarely about mysterious forces appearing. It's about simple laws applied in situations where your intuition is still trained on simpler cases. Gravity doesn't lose. The wheel doesn't cheat. The wheel just obeys a law that is more subtle than your first guess. And that's the fun part.